Morning, folks. Today I'll be talking about RIP encapsulation, or as I like to call it, RIP encapsulation, which is an exploit I came up with in conjunction with my professor, Dr. Matthew Hicks. It's an exploit which breaks the IP encapsulation on Texas Instruments MSP devices. So let's begin. IoT devices are ubiquitous. They can be found everywhere, from military asset tracking and remote patient monitoring to edge computing enabled wearables and self-driving cars. As this chart illustrates, it is projected to become a $1 trillion industry in the next 5 years. As such, these devices are a treasure trove of sensitive information, which makes their security a critical avenue of research. Embedded computing research has led to some very powerful and energy efficient IoT architectures in the recent times, enabling edge computing and data processing applications, which makes the protection of proprietary algorithms and intellectual property an important security requirement in commercial off-the-shelf IoT devices. However, the ubiquity of these devices implies that physical access is more common for these class of devices than for computer class devices. And besides, given the nature of IoT manufacturing supply chain consisting of various third-party actors, the trustworthiness of co-resident software must be scoped properly. So what is all the fuss about TEs? Trusted execution environment is a security feature, as you may already know, that addresses the threat of co-resident software in computing devices. It separates the execution context into trusted and untrusted security domains, where a code residing in the untrusted domain has limited access under specific permissions to the trusted security domain. However, not all TEs serve every class of devices. Intel SGX and AMD SEV serve the more computationally endowed computer class devices, while security enclaves like the ARM Trust Zone and Texas Instruments IP Encapsulation are more lightweight in their design and scope and are intended for microcontroller class devices. IoT class TEs in particular do not generally come with fancy features like hardware memory based isolation or full-fledged hypervisors, mainly due to presence of energy and hardware area constraints which also dictate their designs. However, these IoT class TEs are ideal for the base case of protecting against IP theft of proprietary algorithms. So let's pause for a second and ask ourselves the question, is there even any merit in breaking IoT class TEs? Yes, there is, to prove the challenges that exist today in achieving lightweight trusted computing for the most ubiquitous and potentially security critical class of devices. So one of the most widely deployed low power microcontrollers is Texas Instruments mixed signal processing line of devices. It comes in two flavors, a 16-bit instruction set on the MSP430 and a 32-bit instruction set on the MSP432. The 16-bit instruction set on the MSP430 can also be extended to 20 bits, as in the case of CPU X. So Texas Instruments offers IP encapsulation on their MSP microcontrollers. It is one of the few TEs for low-end devices, which is common to large-scale IoT deployments. As the name suggests, it is meant for protecting proprietary code and data. It is based on the principle of program counter based access control. This is enforced through the memory protection unit in the MSP430 and the system controller in the MSP432, which snoops on the memory address bus and the program counter to prevent any code outside the IP region from getting read or write access inside the IP zone. As such, only program code executed inside the IP region has data access privileges to the IP memory. So during our research, we found two fatal flaws in the IP design. The first one was that when execution leaves the IP zone unexpectedly, the contents of the CPU register file remain. This implies that if we can somehow force IP exits non-destructively, there is a possibility of reconstructing the IP firmware using intermediate register states. The second vulnerability that we discovered allows all code outside the IP zone to arbitrarily branch to instructions within the IP zone. This implies that we can use this arbitrary branch capability to reuse the IP code snippets and bypass read or write access control checks. So let's start building our exploit based on these two vulnerabilities. Context switches occur when the process transitions between high and low security domains. When context switches, a lot of intermediate execution states such as the CPU and peripheral registers, program stack and RAM contents remain unsanitized. As such, it is important that TEs sanitize the execution state on all context switches, which is something IP encapsulation does not do. The other thing to note is that when untrusted code interacts with the TE, it does so by making calls to procedures inside the secure enclave known as call sites. Call site verification checks execute accesses to the callee functions. As such, it prevents program counterflow hijacking and execution of arbitrary commands. This is another important feature which is missing in the IP access control. Now, I'll just give a brief background on code reuse attacks, which you already might be familiar with. Code reuse attacks are useful when injecting malicious code is prevented, like in the IP zone. Malicious gadgets are created by chaining existing code snippets, typically ending in a return instruction, as in the case of return-oriented programming. Gadgets are chained with a manipulated program control flow to execute arbitrary commands and carry out exploits. Now, we have all the ingredients needed to carry out our end-to-end exploits. Not yet. Some challenges still remain. Since we cannot set breakpoints, we need a more creative way to exit and re-enter the IP's zone in an incrementing way. In our initial naive approach, we used debugger halt signals to interrupt the MSP430 IP code execution. However, it was slow with the latency of 250 milliseconds, which is far from single instruction granularity that we want for such an attack. To this end, we decided to use timer interrupts for a way to exit and re-enter the IP in an incrementing loop. However, what if general interrupts are disabled on the IP entry? And more importantly, how can gadgets be identified without any prior knowledge of the firmware binary? Let's address the first three challenges. Taking inspiration from return-oriented programming and replacing the return instruction with a carefully crafted interrupt, we devised a new class of code reuse gadgets we call interrupt-oriented programming. For our interrupts, we use the timer module to interrupt the program at single cycle granularity, which is much better than the single instruction granularity that we were aiming for. This is enabled by the fact that IP cannot protect the fixed memory section containing the interrupt vector table, which gives the adversary the ability to handle interrupts maliciously in the unsecure memory. Now, let's take an example to understand interrupt-oriented programming with a read IOP gadget. Here, we leverage indirect load instructions to read an IP memory address from the unsecure region. Let's assume that we know what the IP protected indirect load instruction is beforehand. However, we shall let go of this assumption when we carry out our end-to-end exploit. First, the adversary sets the source register of the indirect load instruction to any desired IP address they might want to read, followed by a branch to the IP protected indirect load instruction thanks to vulnerability 2. Once the indirect load instruction completes execution, the adversary interrupts the CPU to exit the IP zone and pass the execution control to the malicious interrupt handler, which resides in the unsecure world. Finally, the adversary can read the IP protected indirect load instructions destination register from the register file thanks to vulnerability 1, that is unsanitized context switches. In a similar fashion, we can also leverage indirect store instructions to write a desired value to a desired IP memory address. First, the adversary sets the source address for source register of the indirect store instruction to the desired value they want to write. Then they set the destination register to the IP address they want to write to, followed by a branch to the indirect store instruction in the IP zone thanks to vulnerability 2. Finally, the adversary interrupts the CPU on the execution of the indirect store instruction to complete the write to the IP memory address. Now, we have addressed the first three challenges. Let's tackle the remaining ones. Introducing RIPencapsulation, a set of interrupt-based data-oriented side channel exploits which give the adversary unrestricted read, write, and execute accesses to the IP protected memory. While now we can leverage vulnerability 1 to identify IOP gadgets without a priori knowledge of the IP binary. Vulnerability 2, on the other hand, allows skipping general interrupts, disabling instructions inside the IP zone during IP calls. So now we have all the ingredients in place for carrying out our end-to-end exploits. To understand how RIP encapsulation works, let's take the example of TinyAES encryption algorithm with the aim of exfiltrating the entire TinyAES firmware binary. TinyAES is a lightweight encryption algorithm. In our setup, we store the entire encryption implementation and the 128-bit secret key inside the IP zone as a library function. The unsecure code only passes the 128-bit plaintext to the TinyAES IP function call, and then TinyAES returns the 128-bit ciphertext back to the unsecure code. As such, TinyAES code and the secret key are a black box which we will be attempting to exfiltrate from the IP memory region without any prior knowledge of the TinyAES binary. The entire exploit can be broken down into 3 phases, where the first phase consists of creating a side channel to get the IP code register file dumps at a single cycle granularity. First, the adversary sets up and initializes the timer module. Next, they increment the timer count by 1, enable general interrupts, followed by a branch to TinyAES code inside the IP zone. We don't call the function directly because it has a general interrupt disabling instruction at the start, which we intend to skip to avoid disabling the interrupts. The instruction to branch in the IP zone in order to skip the interrupt disabling instruction can be found by hit and trial looking at the contents of the register state dump. Then the timer module kicks in to interrupt the CPU, and the program control passes to the malicious interrupt service routine residing in the unsecure memory thanks to a fixed interrupt vector table memory section. The ISR copies the register file to some unsecure memory region, then transmits the register dump in the unsecure memory to the adversary's machine using some sort of serial communication. In our case, we used UART. Finally, it resets the status register, the stack pointer, and the program counter to jump back to the malicious code where the timer count is again incremented by 1 so that the interrupt fires 1 cycle later this time and the CPU execution state goes 1 cycle deeper inside the IP code. Enable interrupts again, branch to the IP memory region, making sure to avoid the interrupt disabling instruction. Interrupt, 1 cycle deeper this time. This entire process is repeating in an incrementing loop fashion, and we get the register state dumps of the IP execution state at a single cycle granularity until we reach an register indirect load instruction, which in this case also leaks the key bits from the IP memory as it is part of the key expansion function inside TinyAES. But how will we know what this indirect load instruction is and that it is indeed leaking the key bits when the whole binary was a black box? This brings us to phase 2. After we get all the register dumps, we reverse engineer them to make sense of them. In fact, it is easy to identify the register indirect load instructions in the register dumps. When it comes to register indirect load instructions, we can inject a malicious value in the source register address and check if that value arrives in the destination register after execution of the unknown IP protected instruction. In this manner, we can identify almost all the register direct and indirect instructions except for lossy instructions like the OR operation. Also, it is not possible to identify the memory-to-memory operations just by observing the register dumps, as they do not make any observable changes to the register states. Cycle count can be another useful source of information, as instructions in the MSP430 and MSP432 instruction sets have fixed number of cycles. Patterns are also very helpful in discerning the firmware binary. For example, here recurring PC patterns imply loops. Enabled by phase 2, now we know what this instruction is and we can use it to exfiltrate the key bits. After phase 2, we were able to reverse engineer approximately 60% of the IP protected firmware, but more importantly, it allowed us to identify all the indirect load and store instructions which can be leveraged as IOP gadgets to exfiltrate 100% of the IP protected memory contents. As we discussed previously, indirect load instructions can be used as read IOP gadgets. In order to use the indirect load instruction as a read IOP gadget, we set the source register of the indirect load instruction to a desired IP address and trigger an interrupt after its execution to read out the value of the IP address through the destination register. We will use this read IOP gadget to exfiltrate the entire IP firmware as follows. Again, we set up the timer module, but with the fixed timer count this time set to fire an interrupt after the execution of our targeted indirect load instruction. We set the source register of the indirect load to 1 word below the IP segment start, increment it to point to the start of the IP segment, enable interrupts followed by a branch to the indirect load instruction inside the IP zone. The indirect load instruction completes execution, boom, interrupt. The control passes to the malicious ISR, where we transmit the register dump to the attacker machine, and in this way, we just read the first word of the IP memory segment. If we repeat this process several times, we can read out all the contents of the IP memory segment, including all protected code and data. In a similar fashion, we can leverage indirect instructions as write IOP gadgets to write desired values to desired memory targets inside the IP zone and modify its contents, thus breaking all the guarantees of confidentiality and integrity that IP encapsulation provides. So when it comes to the MSP432, the fundamentals of RIPencapsulation remain the same. But obviously, because they have two different instruction sets, there are some noteworthy differences, the obvious one being different instruction sets. More interestingly, in the MSP432, the interrupt signals stay asserted even after exiting the malicious ISR, leading to immediate firing of reinterrupts. To tackle this, we must stop the timer and clear all the interrupt flags as soon as we enter the ISR. Interrupts also remain active if proper procedure for returning from the interrupt handler is not followed. To tackle this, we write the malicious return address to the main stack pointer, followed by a return instruction so that we can subvert the control flow back to the malicious code instead of the IP code where it was first interrupted. Finally, every time the program counter revisits the IP code from the unsecure code, the system controller dictates that the IP data access must be unlocked by writing a publicly known activation key to the special purpose register. So we had to construct a more sophisticated IP gadget as shown on the right. You can find more details about this in the paper. So for the evaluation, we set up IP encapsulation according to Texas Instruments recommended secure programming practices by disabling all interrupts at the start and clearing the register file at the end of the IP code. We perform all our tests on the 16-bit MSP430 FR5994 and the 32-bit MSP432 P401R. Additionally, we also confirm the efficacy of RIPencapsulation on the MSP430 FR5969 as part of our artifact evaluation. All the source code was compiled using MSP430 GCC. If you need more details on the implementation of the source code, please visit our GitHub repository, which is linked in the paper as well as the artifact evaluation. In our evaluation, we found that all our test benches compiled across every optimization level was vulnerable to RIPencapsulation. We were able to reverse engineer up to 60% of the IP firmware on average using phase 1 and phase 2 of the exploit, which was just enough to find the key leaking instructions. Additionally, we found read and write IOP gadgets in all the test benches, and hence we were able to exfiltrate 100% of the IP encapsulated firmware binaries. The entire end-to-end attack to exfiltrate the IP encapsulated secret takes as low as less than 120 seconds for the tiny ES to a maximum of approximately 45 minutes for Gladman SHA 256 due to differences in the number of dumps and reverse engineering effort required, which is fully automated, by the way. And we could have also used different serial communication for this because we used UART at a baud rate of 9600, which is, you can also bump the speed up that way. So in addition, we were also able to find a real-life GPS tracker application and confirm the presence of IOP gadgets in it to show that it is susceptible to RIPencapsulation. This validates our IP theft or imitation threat model where a competitor or a researcher might use the licensed security critical library APIs in their own development code and try to steal the IP encapsulated firmware. Concurrent work by Martin Bognar from KU Leuven who will be presenting at USENIX, showcases how primitive used by RIPencapsulation in conjunction with the call corruption vulnerability can be transformed into yet another end-to-end exploit on the MSP430 IP. So you can check that out as well. Finally, before I end this talk, I would like to reiterate the idea first presented in Aegis architecture, that the privacy of registers and on-chip caches should be protected by trusted computing base from software attacks. As such, call site verification at IP entry and residual context clear up at IP exit is of utmost importance to prevent RIP encapsulation and related exploits. So, are there any patches for this? Of course there are. It's a simple patch. In order to patch up MSP IP, one must save the register file to the protected memory and clear it before every exit from the IP zone, just like Aegis advocated 20 years ago. Use an ARM trust zone like gateway veneer between calls from regular to secure processes. Now, this would patch up the two vulnerabilities which enable RIP encapsulation. However, it is important to remember the resource constrained nature of MSP devices and similar IoT class devices when designing a secure solution for IP encapsulation. That was all from my side. Thank you for listening.